Alright, so what we're going to do here is take a book problem 4 out of section 4.5 in the Stewart Calculus book, number 17, and you're going to graph the curve. Alright, and they give you a rational function, y equals x squared over x squared plus 3. And the little bit of red you see there, it's going to be the first derivative before we simplify. Before I even start, we should be able to look at the board. And is there any way for the denominator to be 0? The answer is no, there's not. So the domain of this is all reals. It has no vertical asymptotes. I don't know the range. I don't care. Okay. I see that it goes through the origin by plugging x equals 0 in. So for the y-intercept, I get the point 0, 0. All right. That's easy to do too. And if we look at this and we remember how to find the horizontal asymptote, what's the limit as x goes to infinity of x squared? It's 1, right? And again, this is from lesson 4.4. All right. So those are all really cool facts for us. All right. And obviously, if I know the x-intercept, if the y-intercept is 0, 0, I know the x-intercept is also 0. So those are all cool little facts. But I'm also interested in the mins and maxes, right? The first derivative and the second derivative are our tools to get there. So we look at y equals x squared over x squared plus 3. F over g, right? Quotient rule. F prime g minus g prime f over g squared. All right, and again, if you're struggling with this, you need to practice, all right? I'm going to circle stuff, all right? F, G, all right? F prime G minus G prime F. All right, guys? That's our first step. I'm going to get rid of all the circles because it kind of mucks it up. But I think at this point we're getting good at quotient rule derivatives. All right? If you're not, you actually probably have to write it out. Okay? Derivative of x squared is 2x times the bottom minus the top times the derivative of the bottom is 2x. All over the bottom squared. I don't want to deal with this, so I'm going to have to simplify. And I see it's 3x cubed plus 6x minus 3x cubed. I'm feeling pretty good about life when I see that. Yeah, 3x cubes go away. Boom. Oh, 2x cubes. Thank you. Doesn't matter because they're going to cancel out. No math there. So what I'm going to get here for y prime, I'm just going to put it up here so I can keep board spaces. 6x over the bottom square, which was x squared plus 3 quantity squared. All right, and that's kind of neat. And again, first thing we want to do is have the critical points, where the first derivative is either equal to 0 or undefined. Now, it's not undefined anywhere because the same thing. It has the bottom of x squared plus 3. We can't make that 0, right? No way, no how. The top can be, y prime can be 0 at what? 0. So 0 is not only the y-intercept, it is a critical point. Boom. And if I was just asking you for critical points, you would be done. So it's either, it could be a local min, could be a local max, could be nothing. All right? So I'm going to box all this up as one thing. I'm going to make it a lot smaller. There it is. I'm going to keep it a little bigger so I can read that y prime is 0 at 0. That's the only thing I really needed out of that. Now I need to do the second derivative. And I'm going to use it of the first derivative. I got to do the second derivative, right? It is, again, two ways to handle it. Most students would look at that and do the quotient rule. You could also handle it as a product rule. 6x times the quantity x squared plus 3 to the negative second power. But I'm going to handle the quotient rule because that's how most of you would do it. What's the derivative of 6x? 6. The bottom is x squared plus 3 quantity squared minus 6x. The derivative of the bottom, x squared plus 3 quantity squared. Got to bring the squared down. Reduce the power by 1. It's a chain rule, right? And then the inside derivative is 2x. All over x squared plus 3 quantity squared squared, which is to the 4th. Now, everybody, the reason we want to practice and talk about this problem is before you start distributing, I want you to see a single term in the bottom, and I want you to see two terms in the numerator. And then I want you to see that the sum, x squared plus 3, is common before we start distributing. I have 2 of them here in this term, I have 1 of them here, and I have 4 of them in the bottom. We are pretty good algebra students, being in calculus. So I'm just going to cancel 1 of them out immediately. Alright? And it makes our lives much simpler. Look at what happens to the numerator. Instead of having a squared, I have a single power. So I can write y prime prime. I'll distribute the 6. 6x squared. Let's make sure I don't make a math mistake. 18. 6 times 2 is 12x times 2. It's minus 24x squared. All over. Quantity x squared plus 3 to the third. 6x squared minus 24x squared is negative 18x squared. You guys agree? I'm going to do 2 steps at once because that's what college professors do. I'm going to fall to negative 18 and write x squared minus 1. And I do that for a reason, obviously, because when you look at that, your first instinct should be, oh, I see where the double derivative y double prime equals 0 at 1 and negative 1. Bottom can't be 0. So I go y prime prime equals 0. Where? At x equals plus or minus 1. Possible points of inflection. Most likely, right? Possible points of inflection. Alright, so once again, I box all this stuff up because I haven't done anything yet. These are all just the tools we need. Oh no, I didn't box it all up. Let's try that again. Alright? Because we're gonna want to look at this stuff later. Alright, so I'm going to put that here with that. Alright, so now we know what's happening. We have a function, y in black there, equals x squared over x squared plus 3. It's rational. We know its horizontal asymptote is 1. We know it has no verticals. We know the domain's all reals and it goes through the origin. We know it has a critical point at x equals 0. And it has 2 points where the second derivative is 0 at plus or minus 1. It is sine table time. Whoop. Here we go. If we weren't having fun already, it is now going to get almost unbearable. I might have to move the whole thing to make some notes here in a second. Okay? So, I'm feeling pretty good about life. Alright, do we agree that 0, 0 was the intercept, and we know that it was also 0 there, and then the second derivative is 0 at 1 and negative 1. Alright, so I think some of the confusion here, I'm going to try to remain with it, is that I see 2 regions where I have to deal with the first derivative. I see 2 regions I have to deal with on the first derivative, on either side of 0. I see 3 regions I have to deal with on the second derivative. Okay? The first derivative is going to tell us increasing, decreasing. The second derivative is going to tell us concavity. So we're going to start there, and then we're going to use the first and second derivative rules to find the maxes and mins. So I look at the first derivative over here. 6x over the quantity x squared plus 3 quantity squared. Forget the bottom. Something squared is always positive. You guys agree? It can't be 0, so we're okay. So the only thing we got to decide is look at the numerator of 6x. Well, to the left of 0, it's negative. To the right of 0, it is positive. This function decreases to the origin and then increases out. All right? If I ask for that region. So maybe we'll do those intervals here at the bottom too. Next thing up would be to look at concavity, which we do in this derivative. Now this one's a little more complicated. But again, we agreed the bottom can't be anything but a positive, right? X squared plus 3. And I don't care if you cube it, right? Doesn't matter. So I only have to look at negative 18 times the quantity x squared minus 1. So I'm looking right here. And I'm plugging in values. And I think of like negative 1 million. Yeah, well, it goes negative, positive, negative. All right? And if you're not sure, take your calculator. All right? And I'm going to pause the video and get a calculator. I just grabbed the calculator, and I put it up here on the screen over everything we had. And I take negative 18 times the quantity 10 squared minus 1 to the right. And if I hit enter, it comes out to be a negative number. That's what sets the negative region, all right, guys? And you can do that for all three regions, and that gave me that negative, right? And if you're not sure about the denominator, put the whole thing in. It just takes a little time. You'll get better with practice. This tells me that it's concave down, and here it is concave up. So I really got a lot of information about this curve. I'm really kind of interested in the max and min, so I'm going to do that here as a note section in blue. The first derivative is 0. The second derivative is positive. All right, picture a 0, flat, and then you know it's concave up. We know that by the second derivative rule that this is a local min. All right. Likewise, I could probably prove it that the first derivative, it goes from negative to positive, right? Negative to positive, that also proves it's a local min. All right, I have enough now to do the graph. I'll box all that up. I have enough to do the graph. All right. Goes through 0, 0. 1, 1, 1, 1. All right. And if I want to know the values at -1 and 1, I can put those into the original function up here, and I can quickly do the math. I'm pretty good at math. It's 1/4 and 1/4, so I know that these points are right here, and I'll put them in. I wouldn't have to be exact. I knew that this function was, all right, and it approaches a horizontal asymptote, right, of 1. So the function, I'm going to do it in red, and I'll make these points a little dark in red then. So it's coming from positive, right, concave down. See how it's concave down? I drew the tangent line. Now it goes to what? Concave up. If I exaggerate through the origin, then it goes back to concave down. Now, first of all, someone should have yelled at me. I didn't need to do the whole thing, because what kind of function was this at the very beginning? No. Even. It's symmetrical across y-axis. I only had to do half of this thing. I did the whole thing. I'm dedicated to calculus. All right, but now I've proved it, and that's what this curve looks like. And it makes sense if you think about x squared divided by x squared plus 3. When you get really big, does plus 3 ever matter? Not a bit. And it does something funky by the origin. And there's our curve. It has a. And now, what can we tell from the graph? From the graph, we can tell that our local min is a global min, or an absolute minimum, right? The other thing we can tell is I could do the range now if I had to have it. Yeah. I think it would go from 0 to 1, but not 1. And that would be the graph of this function. All right, using calculus, you could check it. We could talk about the regions of increasing, decreasing from negative infinity to 0, increasing from 0 to infinity. And we talked about the regions of concavity. Concave down from negative infinity to negative 1, concave down from 1 to infinity, and concave up from negative 1 to 1. So we have 2 points of inflection. Negative 1 comma fourth, and positive 1 comma fourth are our 2 points of inflection. And we have just done rational function curve sketching through calculus.